for this program is provided by Annenberg CPD to advance excellent teaching.
Everybody likes to talk about the weather, and usually that means the temperature. No matter whether it's a frigid night in February or a torrid afternoon in August, the temperature is an inescapable part of our lives. And yet all that beautiful physics that Professor Newton taught us seems to have very little to say about temperature. But there is a connection. If I lift this block, I'm doing work against gravity. Once I've done it, the block has potential energy. If I release it, the potential energy will immediately turn into kinetic energy. But look what's happened now. The kinetic energy is gone, the potential energy is gone, and my work is gone. Now, I'm not one of those people who thinks that nobody appreciates his work. But what happened to it? The answer is it turned into heat, the random motions of atoms and molecules. And the evidence for that heat is the fact that the table is just a little bit warmer now than it was before. And so, there is some connection between temperature and the motion of atoms and molecules. And that connection is our story for today.
A long time ago, scientists concluded that heat is the random motion of atoms and molecules.
You're listening to KNT, Radio KNT, Hot Springs.
But the average person doesn't need science to tell him when it's hot or when it's cool.
At 25 before the hour, the mercury has passed 112, and where she stops, nobody knows. But let's get back to the mellow sounds. Brought to you this afternoon by Packard, the motor car of the station.
One way or another, temperature affects everything on Earth. Practice and memory, intuition and experience, taste and touch. They all provide a very practical sense of temperature. But knowing, rather than feeling, how hot or cold it really is, calls for some sort of objectivity and some form of quantification. And that calls for some tools of science. A thermometer, for example. One of almost any variety. The style doesn't matter much, as long as it works. Finding an accurate means of measuring temperature can be a challenge. Sometimes it's hard to get a handle on temperature. For one thing, since it lacks physical dimensions, there's no way to measure temperature directly. While the length of an object can be expressed in meters and its mass in kilograms, temperature can be measured only in terms of its effects. And temperature can be measured effectively only when there's an accepted scale. Whether seen on a Fahrenheit scale, which is still the predominant way to view it in the United States, or on a Celsius scale, temperature scales are effective scientific scales because they offer standards for comparison. One useful calibration point is the freezing point of water. On the Celsius scale, water freezes at 0 degrees. On the Fahrenheit scale, it freezes at 32 degrees. Another reliable calibration point is the boiling point of water. On the Fahrenheit scale, it boils at 212 degrees, and it boils at 100 degrees on the Celsius scale. But water and people aren't the only things affected by temperature, no matter how it's measured. Temperature can also affect pressure. Pressure is the force per unit area exerted, in this case, on the fabric of a hot air balloon. Obviously, pressure is affected by heat, but that's not the only way to blow up a balloon. How does gas blow up a balloon? Or for that matter, how does it exert pressure against a solid wall? Each time a gas molecule hits a wall, it gives the surface a tiny push. And of course, by bouncing off the wall, the molecule changes its momentum. The change in momentum means a force must have acted on the molecule. And of course, that means the reverse force must have acted on the wall. As more and more molecules strike the wall, the individual pushes begin to merge. At an almost unimaginable rate, even within an ordinary gas such as air, there's a steady drumbeat of molecules, a constant, uniform pressure against the wall.
This phenomenon is illustrated by a computer calculation of a kind often used today by scientists to help them do research. In this case, the piston and each atom are programmed to obey Newton's laws and then set free. The piston is falling as if under the influence of gravity, but it's held up by the atoms colliding with it. The mass on top of the piston shows how big the pressure is. This kind of calculation is called a molecular dynamics simulation.
A molecular dynamics simulation can even help to explain why fuel is needed to keep a hot air balloon aloft. Heat is the energy of random motions of atoms and molecules. Heating a gas increases the kinetic energy of all the molecules. When a gas is hotter, each collision exerts a greater pressure on the wall. That's why heating a gas increases its pressure. Or conversely, That's why it takes less gas to maintain the same pressure. Here, because of the heater, fewer air molecules are needed to provide the balance of pressure from inside the balloon. It weighs less than the same volume of air would, and that's what gives the balloon its buoyant spirit. In the spirit of science, reduced to its essence, it all comes down to force and momentum, action and reaction. Isaac Newton wrote the book on force, momentum, action and reaction, and the book had something to say about the pressure and volume of a gas. In fact, what it said proved to be surprising, because it proved that even the great Sir Isaac could be wrong. The correct explanation, firmly based on Newton's laws of mechanics, but not on Newton's theory of gases, was provided by 19th century scientists named Joule, Maxwell, and Boltzmann.
Expressed in modern terms, they found that the pressure in a gas is proportional to the number of molecules and inversely proportional to the volume. And it's also proportional to the average kinetic energy of a molecule. By applying Newton's laws of motion to the individual gas molecules, they found that the constant of proportionality is simply 2/3.
This great theoretical insight came in response to an ever-expanding experimental knowledge about the nature of gases. In the 1600s, when the dividing line was thin indeed between science and witchcraft, it took an unusual researcher to rise to the challenge of invisible gases. He was a chemist as well as a physicist, often accused of putting too much physics into his chemistry. His name was Robert Boyle. For a decade and a half, he worked in his laboratory at Oxford. More than his contemporary, Isaac Newton, Boyle's approach was ahead of his time. He hired assistants and emphasized the scientific method. But unlike Newton, Boyle was accessible to the public. Until his death in 1691, London society came to view Robert Boyle as one of the more popular scientists of the day. Boyle was one of the first scientists to practice the quantitative approach. He noted everything in detail, which permitted others to repeat, to verify, and to advance his research. Boyle's practice became universal and universally practiced as the scientific method. For the most part, then, Robert Boyle went about his scientific business with the greatest care. And in doing so, he discovered that at a fixed temperature, the product of the pressure and the volume of a gas is nearly constant. As long as the temperature of a sample of gas remains unchanged, the pressure is inversely proportional to the volume.
The experimental equation, PV equals a constant, is known as Boyle's law. The application of mechanics to the properties of a gas explain the inner meaning of that law. The constant in Boyle's law is equal to 2/3 the number of molecules times the average kinetic energy per molecule. In other words, PV is proportional to the total kinetic energy of all the molecules of the gas. That kinetic energy is a form of heat.
Therefore, Heating a gas either causes its pressure to rise or its volume to expand. And heating a gas can also cause its temperature to rise. So temperature is related to pressure and volume. But how? How indeed, wondered Monsieur Jacques-Alexandre César Charles. Charles was intrigued by the hot air balloon flights of the famous Montgolfier brothers, the pioneers of hot air ballooning. On December 1st, 1783, Charles took the second balloon flight in history. And as a pioneer in science as well as space, he began experiments to explore the nature of gases. Charles's curiosity led him to the discovery that all gases expand by the same amount, with a given rise in temperature. Charles discussed his lofty but unpublished discoveries with Joseph Louis Gay-Lussac, another French scientist and balloon enthusiast who was now able to soar to new heights, an altitude of 4 miles. Publishing his own work, Gay-Lussac described, criticized, and considerably improved upon Charles's discovery. At a given pressure, the volume of a gas, any gas, changes by the same fraction for each degree rise in temperature. If that behavior remained true, there could be a temperature so low that a gas would occupy no volume at all. As the gas warmed, its volume would increase in proportion to the temperature. Of course, the reason the volume increases is the increasing heat or kinetic energy of the molecules. This idea led to a new concept of temperature itself. It would have an absolute meaning based on the universal properties of gases. And absolute zero, the lowest possible temperature, would be the temperature at which a gas would be entirely without heat. According to Charles and Gay-Lussac, absolute zero would occur at 273 degrees below 0 Celsius, or 459 degrees below 0 Fahrenheit. The idea of an absolute temperature was given its final form by Lord Kelvin, for whom the absolute or Kelvin temperature scale is named. On the Kelvin scale, the temperature is directly proportional to the volume of a gas, as Charles and Gay-Lussac said it should be. But twice as much gas must occupy twice the volume. In other words, volume must also be proportional to the number of molecules of gas. Boyle's law states that at any constant temperature, PV is constant. But if T changes, that constant must also change. So, PV is proportional to NT, whether N and T are constant or not. The constant of proportionality, K, is defined to be equal to 1.38 times 10 to the minus 23rd joules per Kelvin. This definition determines the size of 1 Kelvin, and with it fixes the whole Kelvin temperature scale. For example, ice melts at 273 kelvins. And the boiling point of water is 373 kelvins.
Well, I'm here. I wasn't sure she'd even make it. Look at that. I tried driving slower and that made it worse, and then I tried driving faster and that made it worse.
glad I found a station with the mechanic, so you can have a. Tell you what, I'll bring it up front so you can look at it right now.
Room temperature is about 300 kelvins.
Oh, mercy. I was afraid of this. I think it must be overheating. In fact, I'm almost sure it is.
The surface of the sun, 6,000 kelvins.
I had a whole crate of encyclopedias, and I had to throw them off just to lighten the load. I'm so happy that I found this here and you, because you're the mechanic.
And the temperature deep within the sun's core is 15 million kelvins.
This isn't too busy either. Boy, you look like you fixed about 100 cars already today. Why don't you check it out? I've been working here in town. You know, the people are really friendly, but the houses are so far apart, and it's a lot worse than I thought it was going to be. Oh, little boy, please don't do that. Please don't. This car is having a very hard time as it is. Thank you so much. If you can go ahead and do your work, I'm going to have to call my boss.
Closer to the Earth, the experiments of Charles and Gay-Lussac suggested that since gas can be compressed, gases must be composed of discrete particles separated by a void. Applying the laws of mechanics to those invisible molecules leads to the kinetic theory of gases, which says that the kinetic energy of a gas, that is, the collective effect of molecular collisions, is what gives a gas its pressure and volume. But pressure times volume is also related to the absolute temperature. And so at last, there's a direct and simple relationship between temperature and heat. The absolute temperature is given by 2/3 the mean average kinetic energy of one molecule of gas. And of course, heat in a gas is just the average kinetic energy of its molecules. In other words, heat and temperature can be related to a mechanical property, the kinetic energy, of individual molecules of gas. Again, no matter where they rise or fall, all temperatures are related to the pressure of the gas by the equation PV equals nKT. This equation, vital in both physics and chemistry, is called the ideal gas law. Not all gases are ideal, but the ideal gas law nonetheless accurately describes how numerous real gases behave. More than a mere definition of the absolute temperature scale, it expresses both Boyle's law and Charles's law. And it leads to a kinetic theory of temperature.
I don't suppose you know anything about cars, but look, if you do, you speak right up, because that's for sure. You know, I'm an encyclopedia salesman, and I'd show you some of the stuff that I carried, but I had to throw the whole screen off.
And those sweet sounds bring us right up to the hour here at KNT. That's Radio KNT. And now, a word from our sponsor.
In the United States, we use something called the Fahrenheit temperature scale. I've heard lots of silly stories about how that scale came into being. Let me tell you how it really happened. Daniel Fahrenheit was not a scientist at all. He was a Polish merchant who, during the 1700s, decided to train himself in the newly emerging craft of scientific instrument making. And being very clever, he saw a future in calibrated thermometers. He heard that a Danish astronomer named Olaus Rømer knew how to do the job, And so he traveled to Denmark to see how Rømer calibrated his thermometers. Now, Rømer had invented a temperature scale of his own, which, like that of Celsius, was based on the freezing point and the boiling point of water. But the scale had a number of differences from Celsius. First of all, Rømer based his scale on 0 to 60 degrees rather than 0 to 100. The 0 to 60 degrees probably had something to do with the degrees in a circle. The second difference was that Rømer didn't like negative numbers, and so in order to avoid them, when he dipped his thermometer in freezing water, in water and ice, and made a mark on it, he didn't mark that as 0 degrees, but rather as 7.5 degrees, leaving 1/8 of his scale below that. Now, on the day that Fahrenheit came to watch Rømer calibrate his thermometer, Rømer was making thermometers to be used for meteorological purposes, for the weather. And if you're going to make a thermometer for meteorological purposes, it's not convenient to have one that reads from the freezing point of water to the boiling point of water, because the weather seldom gets this hot. And so what Rømer did was to make one mark at the freezing point, and for the other mark he measured human body temperature. And when he had found that mark, he called that 22.5 degrees. And that was the basic scale that Fahrenheit adopted. But Fahrenheit didn't like fractions. So when he made his own thermometers, he multiplied everything by 4. And now the scale was 30 degrees to 90 degrees from the freezing point to blood temperature. Then he made another change. He decided that it would be more convenient to have 64 degrees between these 2 points instead of 60. The reason is a good instrument maker's reason. He had to engrave single degree marks on his thermometer. If it was 64 degrees between his 2 calibration points, then he would divide it in half and in half again and again 6 times, and he would have it down exactly to 1 degree markings. So he shifted his temperature scale once more to make it 32 degrees to 96, a difference of 64. Then using that thermometer, he measured the temperature of boiling water, somewhat inaccurately, not very well, and he decided that it was 212 degrees. Later on, after he died, 212 degrees was defined to be the temperature of boiling water, and that shifted the temperature of the body a little bit. It's really 98.6 degrees. And that's how the Fahrenheit scale came into being. Now you might ask, which of these temperature scales is the best one? That's a silly question. The Kelvin scale, or absolute scale, is the one that's used by scientists. The Celsius scale is almost ideal for cooking because it's based on the temperature of boiling water in an open pot. And the Fahrenheit scale, which has 0 to 100 degrees as the range of normal weather temperatures, is almost perfect if you want to talk about the weather. Well, that's it. Don't forget your galoshes. I'll see you next time.
Funding for this program is provided by Annenberg CPD to advance excellent teaching. For information about this and other Annenberg CPD programs, call 1-800-LEARNER and visit us at www.learner.com.